Okay, hello, this is Jim Plank. This video is going to just walk you through the C++ classification application. There are a couple of videos on this. I urge you to watch them all, but this is kind of the starting video. So let's just go to the framework and go to the CPP apps directory. Now, to compile the classification application, this is the directory where you should be. Okay, and you could say make app equals classify, proc equals risp. I always, if you haven't done it for a while, I'd start with all clean because that'll remove all partial compilations, and then you can do this and start compiling anew, which will take a minute. On my Mac here, my Mac's pretty fast, but there are a bunch of things to compile. So when you're done with this, you will end up with an executable, which will be in the bin directory, again, of the CPP apps directory. There we go. Okay, so there it is, classify RISP. Now, the way the classification application works is you need to give it a data set and a set of labels. The data set needs to be composed of observations, and then the labels will say what your classification categories are. Let's take a look at one of these, standard one. So here, let me go to CPP apps. I'm going to go into the applications directory, subdirectory. You don't typically need to do this, but it makes life a little easier here. So to go to classify, and there are data sets here. That are in a bunch of categories. If we look at the regular ones, you'll see there are a couple. We'll look at the iris one. So this is a standard data set from the 1930s on some parameters of iris flowers. So if we take a look at that data set, well, here, let's just WC it first. Right, you'll note it has 150 lines. There are 150 observations. The label set has the labels. That also has 150 labels in it. If we take a look at the observations, so let's just take a look at 10 of these, right? You'll see there are 4 numbers, comma separated. There could be spaces in there, okay? Each observation is composed of 4 features, which are flower features, and these are used to classify the flowers. The labels themselves, let me just vim this, okay, are in this case just numbers 0, 1, 2. They don't have to be numbers. They can be strings. But what you have here is 50 of each. So here's line 50, there are 50 zeros. If we go to line 100, there are 50 more ones, and then there are 50 more twos. And that's your classification data set. Now, to use the classification app, you need to create a parameter file which is JSON. And typically, it's best to work here in the CPP apps directory. And typically when I do this, I work either in the CPP apps directory or I just work in my own repo and just make calls out to the framework. That takes a little bit more work, but I'll show you that workflow in a separate markdown file / video. Okay, there is a parameter file for iris flower classifications that I've made that is here in the CPP apps directory. So it should be in params, classify iris. There it is. Okay. Now, I've got a tool to help you create these files, but let's just walk through it, right? Here's my data file. There's the label file. Regular just means these are regular observations, regular features. I'll go over what time series ones look like later. The feature specification is optional. If you don't include it, then the program will create it from the data. Once you've done that, though, it's best to specify it in your JSON file. And the reason is because that way you're not recalculating it from the data each time. That way, if you only work on a subset of the observations, you know what the domain of the observations is, and that's important. Okay, so it's good to have these lines in here. The fitness, you can do accuracy or a macro / balanced F1 score. I'll go over that. And then you can specify how to split the data. So What this says is I'm going to split my data 50-50, 75 observations for training, 75 observations for testing, and those will be completely different. So we'll partition the data set into these two. The split type of even, this is a new feature of the application. What it says is when you make this split, make sure that you have the same number of observations in each classification category. So here there'll be 25 of each classification category in the training set and 25 in the testing set. And this is important. If you're going to write about a classification experiment, the experiment makes much more sense if you don't have an imbalance in your observations. And so this ensures that you do have a balance in your observations. You got to specify tests. Typically you don't use it, but you do have to specify it. You can specify it true or false, doesn't matter. Oh, I see I have this twice, so I should make sure that gets fixed. Okay. Sorry, it always throws me when I see a mistake, but I'll fix that. Fortunately, that's not a debilitating mistake. It'll just overwrite regular with regular. Okay, if we want to run the application, let's say we want to run training. We'll run classify app, a train, and then you specify the parameters file with app params. So app params, we can do that. And now it's going to train. One of the great things about the Iris data set is it trains super easily, fast, and it's a very easy data set. So what we've got here is the defaults on the app agent go for 50 epochs and a fairly small population. So it's not the best training run, but it gives you an idea. Here it's nice though, because we've got an F1 score of 90.973. Now, if we want to run this on the testing set, right, that's on the training set. So if we want to run this on the testing set, well, first, the network gets put by default into networks app processor train. Okay, so there's the network. The network has all of your application parameters in it. Now, that's JSON, which is hard to read, but here, let's make it a little easier to read. Okay. One of the things it has in it is it has all of those application parameters. So that means you don't have to specify a file when you're doing testing because it goes ahead and reads what it's doing from the network. Okay, let's go ahead and run testing. So classify RISP, a test, and then we'll specify this network. Okay, and then it will automatically set the data set to the testing data set here rather than the training data set. So we'll see probably a different number than 0.973. Yeah, there we go. All right, now if we wanted to calculate how we got that number, you can show the confusion matrix. Oh, that's going to be an extra app param. So the app agent will let you specify those. Extra app params. And what that does is that allows you to either add to or overwrite the app params that are sitting there in the network file. So that better be a string. Okay, and then this is a Boolean. Obviously, we have this documented in Markdown. So no, we don't want those double dashes. Sorry, off my game today. There we go. Okay, and it shows the confusion matrix. Now, what the confusion matrix is these are the actual classifications, which you notice they add up, the rows add up to 25. On the columns are the predictions. So the neural network predicted label 0 24 times, obviously. It missed one, and it predicted classification 1 28 times. Now, if you want to turn this into an F1 score, you can use the confusion matrix, right? Those are your and with the F1 score, you do it by category. So for category 0, we had 24 true positives. So here, true positives equals 24. 24. And then these are the false negatives, right? Because since this is the actual, this was a mislabeling, which means it was a negative labeling for category 0 because we labeled it on category 1. So that was a false negative. False positives would be in the columns here, not on the diagonal, right? There were no false positives. So equals 0. I know that's not really a command. Oh, that's nice to just set all of those. Okay, and then if you want to calculate the F1 score, here we can do it with awk. The F1 score is going to be 2 times, it's going to be 2 times your true positives, so 2 times 24, divided by the sum of 2 times the true positives, plus 1 times false negatives, plus 1 times false positives. So that should be your F1 score for that category. Okay, 979. Now for category 1, we had 25 true positives. 2 times 25. Okay, plus we had 0 false zero false negatives, but we had 3 false positives. Okay, so that's going to be plus 3. Okay, so that's that F1 score. And then for the last category, they were going to have 23 true positives. And we had 2 false negatives, and then no false positives. So we have that. And then if we want to calculate the actual F1 score, that's going to be the average of these 3. So here, let's go ahead and print that plus that plus that over 3. And we get, boom, that's how we get the F1 score. So that's how you calculate an F1 score. If you wanted to just use accuracy, right, you could do that. Here we'll run it, and then here we'll say fitness is accuracy. Okay, and then we just get 0.96. And the reason that's going to be 24 plus 25 plus 23 over 50, which I assume equals 0.96. Okay, so that's just a little bit of a walkthrough of how you do that. Now, there is a tool in the classification application directory called the classify tool. This is a command line tool. Here you go to make it. Let's just temporarily cd to applications classify and type make utils. That's going to compile that program, and that program is going to be sitting in applications classify bin. Classify tool. Okay, this is a command line tool very much like the network tool, like the processor tool, that allows you to, in this case, kind of query and manipulate files, data files for the classification application. So give it a question mark, it'll give you all the commands. What I'm going to do here is just use it to take a look at a data set. So let's go ahead and look at that breast cancer data set. So here, WC that. Okay, there's the breast cancer data set. You can see it has more observations, more labels. So let's go ahead and take a look at it. The way you look at a data set here is you use the regular or dense or sparse command depending on what the data set is. This is a regular data set. So if I say regular, that, and that, it's going to yell at me. Let's try it again. Applications classify / that. And typically you would. Okay, and then let's get the label set. Sorry, this is kind of clunky. Label.csv. Okay, so it's read it. Now what you can do is you can query. There are a bunch of display parameters here. You can go ahead and query the data set. So if you want to see the number of observations, okay, they're 569, which matches the number of lines in this file. You want to see how many features are in each observation. It's 30. This is a lot of features per observation in this. You can say categories, and it'll say what the labels are. Here they're 0 and 1, just like the iris was 0, 1, 2. Again, those can be strings. If I say features, it's going to spit out for each feature right, what its extent is. So we've got this one, the minimum value is 6.981 and the maximum value is 28.11. Sometimes it's useful to know. It's, as I said, it's good to have that stored in your JSON file. Okay, we look at the observations per category. You'll see that unlike the iris data set, the breast cancer data set is uneven. There are 200 categories with label, 212 observations with category 0, 357 with category 1. Now suppose you want to split this one into a training set and a testing set. What you do to that is there are two split commands. I've got split n and split f. Split n says, well, let's start with split f. Split f says you just give it factors for how you're going to split. Like if I want to split it 50-50, I could say 0.5 in split f. Split n is going to say, I'm going to give the number rather than a factor. Now for either of these, I can give, for training or testing, I can give -1, and that's going to mean just do the remainder of the data set. Random number seed for doing the splitting, and then type is going to be one of random, even, or proportional. Now when I did the splitting for the iris flowers, it was even, which meant I wanted an equal number of observations for each category. Now I could, and that's really the best one you want to do. So if I try to split this, so let's say split f, and let me say I want to do 50-50, even, and here we'll just give it some number as a seed. Okay, it's going to yell at me, and the reason why it yells at me in this one is that, well, I wanted to have I wanted to split this into some number of tests. This sum here is an odd number, right? I did 50-50, but it's going to take half of it for training, the remainder for testing. So the number of testing observations is an odd number. You can't have an equal number of categories with an odd number when you have two categories, so it yells at you. So let's try instead, let's do a split n. And here, let's go with 250 and 250, even, random number. Okay, it's going to yell at me again, and the reason is that I'll look at observations per category. Where is it? It's right there. Right? There are only 212 observations of type 0, and if I wanted to get 250 of each, right, for training and testing, I'm going to need 250 of category 0. I don't have it. I only have 212. So that's a problem. So let's instead, we can do a split. Let's go with, well, here, let's just go with 212 of each type. Okay, even. Boop. Okay, so now the split worked. Okay. Now the way this works is when you do a split in this application, the command line tool, then it's going to have 3 data sets, and you can see them. I could say split status. Okay, so what it's saying is I've created a testing data set with 212, a training data set with 212, and these are the leftover observations. I've got 145 of them. Okay, so now if I want to turn this into a JSON file for the classification application, I could do that. I could do that with TJ, which says to.json. So what that does is that actually spits out the JSON that you can now use in the classification app. And I see it still has those 2 time series things. I'm going to fix that. But fortunately, it doesn't hurt anything. Right, so I can copy that. Okay, here, temp BC text. Copy that, and now I can go ahead and run the classification application on it. So bin classify a train, that file. No. App params, that file. There we go. Okay, and now it's going ahead and doing training on that. Now, another thing you can do with the command line tool, okay, let's go ahead and steal this command again so we don't have to type it in. Okay. And let's go ahead and do the same split. So here, split n 212, 212, even, random number. Okay. What I can do is I can say save split. Actually, I'm not sure if it's, I think it's save TT. Let's take a look at our commands and we'll know. Save, there it is, save TT. Okay. Now with save TT, what that stands for is save the training and testing set. Now that I've done this split, here's split status. Okay. I can say save TT, give it a stem, and so I'll say temp BC. You got to put an XXX into the file name. Temp BC XXX dot JSON. Okay. Okay. So when you do that, what it's going to do is it's going to create 4 files that are going to be temp BC training and testing data and labels. Oh, they're right here. Okay. So what it means is I've now, instead of reading in a data file and splitting it on the fly, now I have data sets that I've already split into training and testing. What this does is it spits out the JSON. You can give it a file name and it'll do that, but it spits out the JSON that will now use this these 2 files. So this is nice because it has the file names in there. It also has the features, and this is important to have the specification of the features because now it can be that the data in these files individually don't have the complete range of features, right? And because it might be those features are actually, the data sets that have those features are sitting there in the unused ones. But since you have specified the features in the JSON file, everything's good. It's an important thing, right? It has the categories, has everything. So now I'll go ahead and if I list stuff, unfortunately these guys are left over, but it just created these data files. Okay. And then if I say here, temp BC, let me remove the old one. Okay. Go ahead and copy and paste in it. Now I can go ahead and train and test on these 2 files. So classify a train map params temp BC.json. Okay. And now it's go ahead and training on that, and then if I want to test, it'll test on the correct one. So if I've been in classify RISP, a test network on that one, there. Now it used the testing set to actually do the testing of that network. Okay, it's a nice feature to have. It's something actually that I prefer doing when I'm doing classification experiments. I prefer to go ahead and split my training and testing data into files and use those files. And the reason is I just like to know what my data is rather than splitting each time. Even though if you give it the same random number seed, it'll split the same way every time. I like having the files myself. Okay, I'm going to go over 2 more things here, and then this video will be over. I'm going to go over the 2 other kinds of data that you can classify on. And these are time series data sets. So let's take a look at here. If I look at dense, okay, these are 2 data sets, which I call shape, it's a time series data set. So again, data labels, 486 means there are 486 observations. But now each observation here is actually a time series of a bunch of values over a bunch of features. So in this data set, I've got 16 features. Okay. Right? 16 features. Each feature is 16 numbers, 0 and 1. And what this is it's a 16 by 16 area of pixels, 0 or 1. And then the observations are shapes that are in different places in that 16 by 16 region. If you want to look at what that looks like, I actually have a picture here. It's in the markdown for this. Right, these are 200 of those 486 points just rendered. So you can see there's 6 different shapes, and they differ from where they are. It's kind of nice because each shape is exactly 28 on pixels, so you can't just count and do your classification. You actually have to do something fairly smart with the classification. Okay. And then the labels themselves, so here if we look at the labels, these are strings now instead of just being numbers. And here let's do a sort-u. There they are. They're 6 different classification strings. So 2 triangles, 2 rectangles, a square, which is hollow, and the cross, which is also hollow. Now, if we want to take a look at this data set in the command line tool, okay, what we do is we can say dense and then give the file names. So here, let's go ahead and rip the directory off here. Dense. Oh, God, my Macintosh drives me nuts. Dense shape data.csv, and then let's also get the label file. Label.csv. Okay. Now, when you do this, you have to give it the number of features here, which is 16. Those blank lines in the file are optional, and so if they're not there, you don't know what the features are. So you have to specify how many features there are here. There's 16. Okay, so num observations. There should be 486 of them. Observations per category. Okay, there are 81 of each category, so 81 different starting positions. If I want to see what the categories are, right now they're strings. Okay, and then this says which when the program runs, it's going to assign numbers to them. And so this is the mapping from the numbers to strings or strings to numbers backwards. If we look at the features, there are going to be a lot of features. There are going to be 16 of them, right? Because there's 16 features per observation. Each one is either a 0 or a 1. Okay, so now let's suppose I try to split these. Now I can't split this one 50-50 either, I don't think. Let's try it. Split f, 0.5, 0.5, even, random number. Yep, it's going to yell at me. Why? Well, because 486 divided by 2 is 243. That's not a number that's divisible by 6. So let's do a split that's, let's say, of the 81 observations per category, let's assign 54 to training, and that would be 27 to testing. So here, let's calculate 54 times 6. All right, we'll do that split. So split and 324 for training. The rest will be for testing. Even, random number. Nice, same random number. Okay. Status, so the split worked. Okay, so now I have the proper number of training and testing observations. Now, if I want to create the JSON for that, I will go ahead and say TJ, and let's just say temp shape text. That'll put it into that file. Okay, so we look at that file. There it is. Has all the information for you. Has the splitting information in there for you. Now, this didn't create training and testing file. I'd have to do save TT for that. This just created the JSON that will read it and do the split. Okay, so now if I want to classify, I can classify. So bin classify a train app params, that file. Okay, and here we go. Now, I'm really anal about this. Whenever you do something like this, you need to figure out what the spikes are looking like. Now, for example, the iris, well, the default encoder for all of the apps, whenever you're running an app created with the app agent, the default encoder in this, well, here we can look at it. Let's see what the default encoder is. It's going to be in the file, in the network. Sorry, so here networks, classify. All right, JDump2. Oh, JDump2. If you want, there is a JDump that you can compile and put. It'll be in the framework here. So go to the framework, make bin JDump. There you go. That'll dump JSON and format it, which is a nice thing to have. Okay, so you can see again, it's got all the proper things in the for the application. Okay, the decoder is a rate decoder with 6 bins. That's nice, right? Winner take all. That's going to count the spikes and over 6 bins and make its decision that way. You'll note the divisor is 50. What does that mean? It means the simulation time of my spiking neural network is going to be 50 time steps. That doesn't seem very smart to me, all right, because I've got a time series with 16 observations. 16 does not divide 50, but the default of the App Agent is always to use a simulation time of 50. Let's look at the encoder. Okay, the encoder is going to have a separate one for each of those features. So there'll be 16 of these, but you notice the interval's 50. Okay, and it's using a spike encoder, right? Which means that 0 will map to 0, and 1, if I'm not mistaken, is going to map to something like, oh no, it won't map to 25. It's going to do the maximum number of spikes, but since you're dividing your interval into 16, it's going to be over like 3 time steps or some crazy number. So it's not, this isn't what you want. What I'm trying to say here is that if I have a time series of 16 elements, I don't want to use a spike-based encoder with an interval of 50. It just makes no sense. Instead, I'm going to want to make either the interval be a multiple of 16, and I might want to change my encoder type. Okay. Now, what you can do with this is you can take a look at the spikes. So here, if we say bin class virus a test, and we'll use this network. Now, let's go ahead and look at the observations. And let's look at the input spikes. Let's pipe that to more so we're not spitting all over the screen. Okay, so the App Agent will show you here are the features, right? The first one here is a cross. Okay, and then what you see is these are the spikes. All right, so the first feature with non-zero spikes was feature 7. So there should be 6 empty time slots, and then there's going to be some spikes, right? You would think there'd be 3 spikes, but since we're using this spike-based encoder, you can see there are a whole bunch of spikes, right? Each one of these ones gets turned into, it looks like 4 spikes. Okay, and you'll see the times are odd, right? 18.75, 19.75. And the reason is because your defaults aren't matching your data set. So what you want to do instead is do something where you change the encoder. So I would, if I were doing this, I would change the sim time to some multiple of 16. Let's make it 64. Okay. And I would say encoder spike, which means each one's going to turn into a single spike. So what this should be now is, for example, this feature here should be just 3 spikes. And then each one of these spikes is going to come 4 time steps apart, because 64 divided by 16 is 4. So here, we do that. Is it doing a better job? Hard to say. But here now, let's go ahead and take a look at the spikes. And now what you see is they make more sense, right? We've got a spike here at 24, another one at 28, another one at 32, and that's it. And that corresponds to these observations. Okay, hate to say it, I know I'm going to sound like a broken record if you ever talk to me. You always have to look at your spikes. Think about your encoder, look at your spikes, make sure they make sense, right? And sometimes it might make sense to use a different decoder. For example, I could say decoder, say rate No, let's not make it rate. Let's make it time to last spike. And I'm not sure if you need to put the number of bins in, so let's just do it. All right, so bins 6. Right, so instead of a winner-take-all encoder, now we have a time to last spike among those 6 bins. And sometimes, especially with temporal data, sometimes that gives you better performance. Training's a rabbit hole. You gotta tweak your encoder, tweak your decoder, tweak your EONS parameters. There's a lot of work you gotta do to get this so that you can get good classification accuracy. But hopefully this gives you an idea of how the application works and how you create your parameter files for it. Okay, last one is going to be the sparse data sets. So here, let's go back to CP apps, applications classify, and look at the sparse data sets. So list data sets, sparse. Okay, I have the shape one here. It's the exact same data set as the dense shape one, but now it's in sparse format. Let's just take a look at it. Sparse format, instead of specifying basically a spike raster for your spikes, you're just going to specify the non-zero ones in terms of feature number, value, time, right? So this one's actually a triangle because there's 1 in feature 6, 2 and 7, 3 and 8, 4 and 9, etc. Right? You end your observations with a blank line, and here's the next observation. You could put more on one line. In this file, the last one, I actually formatted the cross, so it looks like a cross. Isn't that cute? Okay, but this is the exact same data set as before. So now if I want to run on this data set, then I'll go ahead and run the classify tool. Let's say sparse. And that. Let's get the label file. You still have to tell it the number of features, even though you don't really have to. You need to specify it. Okay, so same thing. Num observations should be 400 in those. Let's do the same split as before. So here, split. We'll do 320. Oh, sorry, split n 324 -1 because the rest of them go there. Even again, random number. It worked. Split status. Okay, we're all good. And now let's go ahead and just create a JSON file for that one. So here we'll call it temp. I'll call it temp shape again. Text. Okay, and now you can see it's very similar, gives you everything you want, but now it's a sparse time series rather than a dense time series. But if we want to run the classification training on it, we can actually do the same thing. Okay, because I named the JSON file the same. And same thing, you're going to want to set the sim time to be a multiple of 16. Okay, and put the spike encoder, and again, now it's running.